Hi! In the previous video we have introduced the concept of an eigenvalue and an eigenvector of a square matrix A. Given a matrix A, you have learned how you can check whether or not a given vector is an eigenvector of A and how you can check whether or not a given number is an eigenvalue of A. We have not yet paid attention to the actual computation of eigenvectors that belong to a given eigenvalue. That's what we're going to do in this video, and by doing that we will run into the concept of an eigenspace of a matrix. Let's start with a brief recap. Recall the definition of eigenvalues and eigenvectors shown here. We have seen in the previous video that the condition A times x is equal to lambda times x can be replaced by the more familiar form A minus lambda times I times x is equal to the zero factor. From the theory of homogeneous systems, we know that if at least one non-trivial solution x exists, then there will be infinitely many solutions. This implies that there are infinitely many eigenvectors x that correspond to one particular eigenvalue lambda. Let's illustrate this by further developing our first example from the previous video. We've seen that the number 2 is an eigenvalue of the matrix 3, 2, 3, 8. To find all eigenvectors, we need to solve the system A minus 2 times I times x is equal to the zero factor. The augmented matrix of this system is row equivalent to the matrix shown here. Hence the system A minus 2 times I times x is equal to the zero factor is reduced to the single equation x1 plus 2 times x2 is equal to 0. The solution set is the line through the origin in R2 consisting of all multiples of the vector minus 2, 1. All non-zero vectors in this set are eigenvectors of A corresponding to the eigenvalue 2. The complete solution set, which includes the zero factor, is a linear subspace of R2. This is an example of so-called eigenspace of a matrix, which in general is defined in the following way. The eigenspace of an n by n matrix A corresponding to an eigenvalue lambda is the set of all solutions of the homogeneous system A minus lambda times I times x is equal to the zero factor. This solution set is often denoted by E lambda. You probably have already noticed that this set is actually equal to the null space of the matrix A minus lambda times I, which implies that it is a linear subspace of Rn. Here are some important facts to summarize. Let lambda be an eigenvalue of a given n by n matrix A with corresponding eigenspace E lambda. Then, E lambda is equal to the null space of the matrix A minus lambda times I. Hence, it is a linear subspace of Rn. E lambda contains all eigenvectors of A with eigenvalue lambda, as well as the zero vector, which is not an eigenvector. The dimension of E lambda is at least equal to 1, because if the dimension would be equal to 0, then lambda wouldn't be an eigenvalue. Finally, I'd like to show you an example of a 3 by 3 matrix which has two different eigenspaces of different dimensions. Have a look at this matrix. In the next video you will learn how you can calculate the eigenvalues of a matrix. It turns out that the eigenvalues of this matrix are equal to 3 and 1. Let's determine the corresponding eigenspaces. The eigenspace E3 is equal to the null space of the matrix A minus 3 times I. The matrix A minus 3 times I is row equivalent to the matrix shown here, so it has rank 1. The null space of A minus 3 times I is simply given by the plane with the equation x1 plus x2 plus 4 times x3 is equal to 0. Which can be written as the span of the two vectors minus 1, 1, 0 and minus 4, 0, 1. Hence, the dimension of the eigenspace E3 is equal to 2. What about the other eigenspace, E1? Well, the matrix A minus I is clearly not a rank 1 matrix. On the other hand, we know that the rank should be smaller than 3, so the rank must be equal to 2. Indeed, we find that the matrix A minus I is row equivalent to the echelon matrix shown here, which reveals 2 pivot positions. Hence, the number of the null space of this matrix is equal to 1, so it is a line through the origin in R3. This line can be written as the span of the vector -2, -1, 1. To summarize, the numbers 3 and 1 are eigenvalues of this matrix A. We have determined the 2 corresponding eigenspaces. They turn out to have dimension 2 and 1, respectively. Are 3 and 1 the only eigenvalues of A? If so, how can we know this? Good questions. This will all become clear in our next video, covering the so-called characteristic equation of a matrix.